Alright, so today we're going to be looking at how much heat it actually takes to convert a hunk of ice into gaseous water vapor. And then after that we're going to be looking at this hot metal plus ice example, which is on D2L. So first of all, we're just going to draw out the little curve here, and really once you know the curve, and if you just think about this, how water warms up as it goes through its phase transitions, it actually becomes kind of simple to think about this. Alright, so here we have on the x-axis the amount of heat added. This is just arbitrary units. I'm not trying to plot this out accurately. And over here on the y-axis is going to be our temperature of, and we're going to be dealing here with water, so of course our melting and our boiling points at 0 and 100 degrees Celsius. Okay, so what I've done here is basically just plotted out the amount of heat that's added as we start off from solid water, go to the melting, then heat up the liquid water, boil, and then heat up the steam here. So we're just going to look at these different regions here, and actually they have quite a bit of similarities between them. So first up, we're going to just look here at the solid. So for solid water, the amount of heat added, that's going to be my Q sub S, is equal to the mass of the water times the specific heat of the solid water. So the specific heat is going to vary depending upon the phase, times the change in temperature. And remember, the change in temperature is going to be your final minus your initial. So since we're going to be heating up the solid, well, if we get up to the melting point, it's going to be 0 minus our negative 15, which is our starting point, which I just chose arbitrarily here. All right, the next thing is we're going to be melting this. This is also known as fusion. All right, now when you melt something, that's, like I said, known as fusion. Well, this is, as you can see, there's no temperature change undergoing with the melting. Same thing here with the boiling. So there's no temperature dependence on here. All it is the mass times the enthalpy of fusion, and this is just a number that would be given to you. And this again varies depending upon what substance you actually have. All right, this of course is the liquid. So here again, as you're heating your liquid, this is going to be the mass of that liquid times the specific heat capacity of that liquid times the change in the temperature. So here, if you're just heating the liquid up from 0 degrees to 100 degrees, that temperature change would be 100 minus the 0. So here's boiling or vaporizing, and this is going to be similar to the melting or fusion. So here the heat as you boil this is going to be equal to the mass of the liquid times the enthalpy of vaporization. Again, that's just some number that you can get. And then once you're up here in the gaseous form, well then the heat for the gas is just going to be equal to the mass of the gas times the specific heat capacity of that gas times the change in temperature. Okay, so that's essentially what you do, and essentially you just start wherever you are, and then you just work your way to wherever you're actually going. All right, now as for some values that we see, and the following values are all going to just be for water in its various phases, because this is the examples we're going to be using. Although if you're looking at for different substances, they will have their own unique values for that. And here I'm just rounding to 1 decimal place with this, so we can see the essence of what's going on without getting bogged down with a whole bunch of extra numbers in our sig figs. So here the specific heat capacity of the ice, that's going to be about 2.1 joules per gram degree Celsius. For water, it's going to be about 4.2 joules per gram degree Celsius. And then for the gas is going to be 2.0 joules per gram degree Celsius. The actual values vary a little bit from these, but these are pretty close. And then as for the enthalpy of the fusion and the enthalpy of the vaporization, so the enthalpy of fusion, that's 333 joules per gram. Notice the difference in units. This is just energy per unit mass. And that's because, again, there is no temperature dependence in here. So you're just multiplying by the mass, you get the joules back out. Same thing up here when you're boiling, that's 2270 joules per gram for that one. All right, and the final thing is the mass, and that, of course, just depends on how much you actually have. For our particular example right here, we're just going to say the mass is equal to 50 grams. Okay, that can obviously just vary, but just for our example. So what we're going to do here is calculate how much heat energy it takes to get from negative 15 degrees Celsius up to 120 degrees Celsius. So first of all, we're going to warm up the ice, melt the ice, warm up the liquid, boil the liquid, and then warm up the gas. Okay, and it's really not that complicated. Everyone has seen the phases that water goes through as it goes from cold to hot. So it's just a little bit of common sense with this, and really this is a pretty trivial kind of calculation to actually do. So we'll just start here with the ice. Okay, so what we have here is my mass, which we've just arbitrarily chosen to be 50 grams. The heat capacity, which we have up here, is 2.1 joules per gram degree Celsius. Again, this is for the solid version. And then my temperature change. So notice here we're going from negative 15 up to 0 degrees Celsius. So that's my final is 0. My initial is a negative 15, so it's 0 minus a negative 15. So you just, this is usually where people screw it up, is watching the negative sign here. So just make sure you be careful of that. So that'd be technically 0 plus 15 when you do all the signs correctly. Okay, so this works out to be 1575 joules. And just to show you that all your units canceled out, the grams go away, the degree Celsius goes away, and you're just left here with joules. All right, so at this point, we've warmed up the ice to 0 degrees Celsius. Now we have to melt the ice. All right, so that's just 50 times my 333 joules per gram, which we have right here. And that works out to be, so at this point, we've melted all of our ice. Now we're going to warm up the liquid. Okay, just notice here my delta T is different in this case because now I'm warming up the liquid as we're going from 0 to 100 degrees Celsius. So right here, that's going to be my mass, of course, my correct specific heat, and this is going to be 100 minus 0. So the delta T, just remind ourselves, the delta T is the delta T you're dealing with in this particular phase, not the entire delta T. It's only what you're dealing with in this particular location. That's all you're actually dealing with here. All right, so we work this out and we get, okay, so at this point we've reached 100 degree water, and now we have to boil the water. Also, just one thing to notice right here, notice how much bigger the vaporization energy is relative to all these others. This is 16,000, 21,000, this is 100,000. So the vaporization takes a lot of energy to actually undergo this transition right here. All right, and then finally, we've boiled all of our water away. Now we have just the steam, so we just have to warm the gas from 100 degrees to 120 degrees and find out how much energy that takes. And this one's going to be 2.0. And here the temperature is going between 100 and 120 degrees, so that's why my delta T in this case is going to be 120 minus 100. That's my final minus my initial, and this works out to be 2,000. And then as for my Q total, this is just equal to the sum of all these things here. So basically about 154.725 kilojoules is how much energy it actually takes to raise the temperature of the ice from negative 15 to gas at 120 degrees for 50 grams of water. All right, one little thing just to get away from this here. Notice how much energy it actually takes to boil into steam. This is why steam burns are so bad, because as you have the gas up here, it has to cool down, and then as it goes back and turns into water vapor, all that energy has to go somewhere. And of course, if you get steam on you, the energy from the heat of the steam is going to go into you, and there's a lot of energy right there, and that's why steam burns are much worse than just getting like boiling water on you. So that's the basics of this little chart right here. Again, it's just kind of good practice just to get an idea what's going on with this. I mean, the calculations are fairly trivial, but really it's just a matter of understanding, what happens, right? You have to warm up the ice, melt the ice, warm up the water, boil the water, warm up the gas. It's very simple. All you have to do is just think about what actually happens during normal phase transitions, and then you can easily just calculate these out. And here again, just notice the pattern here. If we're dealing with the in the liquid, the solid, or the gas forms, we use the MC delta T. If we're undergoing a phase transition, it's just going to be M times either the enthalpy of fusion, enthalpy of vaporization, which would be numbers given to you. And again, all these little specific heats and everything, I will give those to you when you actually need them. So now onto this little example here where we're going to be adding some hot copper here that has an initial temperature of 100 degrees Celsius to 10 grams of ice that has an initial temperature of negative 5 degrees Celsius. So what is the equilibrium temperature? Okay. So what we're going to do is assume there's no heat transfer to the outside world, and just assume that all the heat from the copper goes into the ice, melts it, and reaches water, and they're going to be at a nice little equilibrium temperature here. So essentially what we have here is a little cube of ice, and you're putting on top of it a little block of hot copper. So of course what's going to happen is the heat from the copper is going to go here, into the ice, and it's going to warm up the ice until you get liquid water and everything. And then after these things equilibrate, you're basically going to have up here, the copper, and at this point, the little drip of water over here that are going to be at the same temperature. And the whole thing is basically just figure out, well, where is this equilibrium temperature actually going to be? Now, what we're going to do is basically just follow about, how much heat it actually takes to go through each of these little steps that we just went through here. So essentially, we're first going to take this piece of hot copper. It's going to warm up the ice, melt the ice, and then warm up the water until we reach a point somewhere down here. So essentially, the first part is we have to figure out, well, how much energy does it actually take to melt this ice, right? So just writing down the values that we actually have from the problem here. And again, this is all just on the paper, but it just helps to actually see this thing being worked out. So the mass of my ice and the mass of my liquid are equal to 10 grams because, when the ice melts, it's still going to be 10 grams of water, so they're going to be equivalent. All right, the specific heat of the ice is 2.1 joules per gram degree Celsius. We just saw that one. And for the liquid water, is that same thing, 4.2 joules per gram degree Celsius. And then the enthalpy of fusion for melting the ice is 333 joules per gram. So this is how much energy it takes to actually melt the ice. And then on the other side here for the copper, so the mass of the copper is going to be 100 grams, and the specific heat capacity of the copper is going to be 0.4 joules per gram degree Celsius. All right. And we don't have to worry about liquid copper or the enthalpy of fusion or vaporization of copper because the copper is just going to stay in the solid form. So the first thing we want to do is say, all right, well, we're starting here basically at our initial temperature here. So our initial temperature, which is given in the problem as equal to -5 degrees Celsius, and here this initial temperature for the copper is going to be equal to 100 degrees Celsius. So we're just going to figure out, well, how much energy does it take to warm up this ice up to 0 degrees Celsius first of all. So that's the first thing we have to do. Don't try to do this all in one big step. You have to do this step by step, otherwise things just aren't going to work out properly. So here, to raise up the temperature of the ice, this is going to be the mass of my ice times the specific heat capacity of the ice times the temperature, and I'm going to write this as B minus the T sub A. And basically what I'm doing here is I'm using the lowercase a, b, and c and all that to denote the temperature of my ice, and I'll be using the numbers 1, 2, and 3 for the temperatures of my copper. And actually I should put right here, so that should be temperature 1 in this case, and over here for my temperature, this would be my actually temperature A over here. I have the paper right in front of me. That's going to be my T sub A over there. Okay, so we're just going to figure out how much energy that is. And again, since this is ice, we're going to be ending at 0 and then subtracting off, the -5 for this. And this is going to work out to be a positive 105 joules. All right, so that's how much energy it's going to take to warm up the ice to the melting point over here. Okay, so that's for the ice to melt. Now, of course, since this energy is coming into the ice to start melting it, that has to come from the copper. And since the copper is going to be losing the exact equal and opposite amount of that heat that just went into the ice. So the Q of the copper, and this is going to be Q of copper 1, because this is going to be my first step here, is going to be equal to the negative of the Q of the ice. That's, of course, because the heat that flowed into the ice came from the copper. So they're going to be equal and opposite. So this is going to be now a negative 105 joules. And this is going to be equal to the mass of my copper times the specific heat of the copper times the temperature change. So this is going to be my final temperature. So that's going to be T2 minus my initial temperature of T1. All right, and what we're going to actually be doing here is actually solving for T2. So this is going to be equal to my 100 grams of copper times the 0.4. So essentially you just have to go here, solve for T2, and when you do this, we find out that T2 is equal to 97.375 degrees Celsius. All right, now right here is a good way to double check that you following your signs correctly. All right, now just think about this. The heat is coming from the copper and going into the ice. Do you expect the copper to warm up or cool down? Hopefully you said it, you expect it to cool down. And that's what we see right here, is that the temperature cooled down. And if you forgot to flip the sign over here and you still used a positive 105, what would happen is that the temperature would actually end up increasing by about 2 degrees Celsius. So that's why you would know that something went wrong, because if your change in your temperature actually increased that would be bad, because that would mean that, as heat flowed into the ice, the copper got warmer. That violates many laws of thermodynamics. So that's how you basically just know which way your temperatures are going here. So that's the first step. The second part of this is that we're going to look at how much energy it actually takes to melt the ice. So we're going to be looking at this energy flowing from the copper into the ice. We've already got to 0 degrees Celsius. How much energy do we actually need to melt the ice here? All right, so this is the enthalpy of fusion times the mass of the ice. So this is going to be our 333 joules per gram times the 10 grams of the ice. Okay, you don't need a calculator for this one. This is going to work out to be a positive 3330 joules. Okay, so that's how much energy it takes to melt the ice. So pretty easy calculation. Now, of course, just like before, that energy that went into the ice came from the copper. So the Q for the melting here is again going to be equal to the negative Q for my copper 2. Okay, so in other words, this is going to be the amount of heat that traveled out of the copper during this step. So that means that my Q of my copper 2 is going to be equal to a negative 3330 joules. And it's going to be the same thing here, the mass of my copper times the heat capacity of my copper. And now the next temperature that we're actually going to be going from is going to be starting here at your T2 value, but now going down to your T3 value. Okay, so T3 is going to be your final thing over here, minus the T2. And that's going to be this T2 we just found right up here. Because of course, when we heated up the ice, this is where our temperature ended up. And now we're going to be melting the ice, so that's going to be our starting temperature, and we're going to go to another final temperature there. So this is going to be, when you go and actually again solve for your T3 in this case, we end up that is going to be equal to a 14.125 degrees Celsius in this case. Okay, so we're not, of course, done yet. All we've done is we've melted all the ice, and at this point the copper's temperature is going to be 14.125 degrees Celsius. Again, to make sure that you did all your signs right, obviously it got cooler, which it should, right? You put copper on ice, it's going to get colder. If it went up, that just means you again forgot your negative sign there. So at this point, we have basically ice cold water at 0 degrees Celsius. We have slightly warm copper. So we just have to find the equilibrium temperature between these two things here. So here, the Q of the liquid is going to be equal to the mass of my liquid, the heat capacity of my liquid, because again, now we're not ice anymore, we are now liquid water, times the change in temperature. So this is going to be my final temperature over here, so TF, minus TB temperature, which in this case is actually just going to be 0 degrees Celsius, because of course that's where the ice melted at, so that's going to be 0 degrees Celsius. And this is going to again be equal to the negative Q of my copper. Again, you just have to watch our signs, because the heat that's flowing into the ice is coming from the copper here. I'm going to call that copper 3. That's going to be equal to minus the mass of my copper times the heat capacity of my copper times the final temperature minus my T3. And of course, this T3 just comes from right over there. All right, so then it's just a matter of putting in our numbers here. And now for my liquid, that's 4.2. And then this is going to be TF minus 0. So the final temperature is going to be the same on both sides, because that's where we're going to find our equilibrium. And then 0, because of course that was just cold water. And watching our negative sign in there. Okay, and then it's just a matter of solving for TF. All right, and this is the part that sometimes people get hung up on. So obviously this is just going to work out to be 42 TF is equal to now 100 times 0.4 is equal to 40 TF. That should be a negative 40 TF plus 40 times 14.125. So this is just going to be 82 TF is equal to 40 times 14.125. And once you work that out, your TF is going to be equal to 6.89 degrees Celsius. That's going to be your final temperature. So that's essentially it. Basically, you have this entire thing written out in front of you. Stop and think about, what is actually going on with this. It's really not that hard, but it's really a good exercise to make sure you understand, the heat flow following your signs. Use your intuition. What do you expect to happen? If you're doing this calculation and you wind up that your intermediate temperatures over here wind up increasing, stop yourself. Think about what is actually going on. You're putting a hot object on a cold object. You expect the final temperature to be somewhere in between those two values, right? You don't expect, the copper to start spontaneously heating up. It simply would not make any sense. And really, the one thing I can just tell you, the piece of advice, just practice, practice, practice. Go off this, and again, just don't copy this down, but just start off with this beginning part right here, and then just work it out step by step. It's very simple equations. They're actually quite trivial, but you just have to think about how the heat is actually flowing in here, and then it becomes quite easy. All right, and if you were doing this problem for a different set of conditions, and let's say for the second part you wound up here that your intermediate temperature wound up to go lower than 0 degrees Celsius, what would that mean? Essentially, it would mean that the copper just didn't have enough heat to melt all of the ice. So you simply just melted part of the ice, and then the copper reached 0 degrees Celsius, and it stopped. So that's all that was really going on in that case. But essentially, if you have these kind of initial conditions here, you will find out, this is going to be your final temperature. So really, it's not that hard. You just need to stop, think about where all these values are actually going, and really it's kind of trivial once you just practice this a couple of times. And really, it's a good way to see if you understand the following of the heat flows and everything. And this is all related to this part right here as well. If you just think about it, we started down here with the ice. We started up here with a bit of copper, and what essentially happened was we just cooled down the copper here, and then we heated up the ice until eventually we found this little equilibrium point here where the both things matched up. Okay, so really just to kind of draw out a little graph here, what was actually happening. Okay, so essentially what's going on here is that, oops, draw off the curve here. Okay, so essentially what's going on here is that the copper was cooling down, the water was warming up, and essentially what we found out here was we started up here at 100 degrees Celsius, and then we cooled down this first part here to 97 degrees Celsius, and that was the amount of temperature that it took to go from the -5 up to 0. Okay, so that's that first part here. So that's that first thing we did, and then of course we melted the ice, and then once we did that, we got down here to 14 degrees Celsius or so. And this was where we were at this point, right? So that's when we melted all the ice, we got down to the 14 degrees Celsius. And then, of course, what happened is we just didn't take the average because, of course, the specific heats between the water and the copper are very, very different. So it's not just going to be a simple average in that case. So then what we did was we took this here, and then we just matched up in between, and we got here our equilibrium temperature of the 6.89 degrees Celsius. So essentially the amount of heat that was removed was equal to the amount of heat gained by the ice and the water, and we've reached this equilibrium point here at 6.89 degrees Celsius. So that's all that was happening, is that the amount of heat was just traveling equal and opposite directions, and we wound up at an equilibrium temperature where the amount of heat between them was actually equal. Again, practice this. Hopefully this will be of some use, and anyway, I will end this here.